if I was going to point to one numerical method that was the gem of this semester, I would say it would definitely have to be finite difference frequency domain. It'll be like the other methods. We're going to have equations flying all over the place, but it's going to reduce down and become something very, very simple to implement. And it's incredibly powerful. It's going to let you see the fields. It's a really, really, really neat method. So our research group, we have all of these different numerical methods at our disposal. We have all the off-the-shelf software, and we routinely go back to finite difference frequency domain to do things for us. It's a really, really neat method. A lot of what we've been learning this semester is now going to come together and let us implement this. So all of our talk with periodic structures and diffraction gratings and calculating transmittance and reflections and finite difference method and Maxwell's equations, it's all going to come together and let us implement this method. Before we dive into the formulation, I want to talk a little bit about the periodic boundary conditions. There was something we left out last lecture intentionally because I wanted to cover it now, that we need to add to incorporate periodic boundary conditions the way we'll need it for finite difference frequency domain. And then following a parallel path to our other formulations, we're going to derive matrix wave equations. We're going to learn how to incorporate now a plane wave source. You'll build a device on the grid, define your source, and when you calculate the fields, it will calculate as if that source has now bounced off of your device and is going all over the place. I will summarize the formulation and give you some quick examples to try to give you a feel of what this is going to look like when you implement it. What's your data going to look like? And then we'll end with, once you have your fields calculated, how do you calculate transmittance and reflectance? So remember what we did last time. We started with Maxwell's equations, we approximated all of the derivatives with finite differences, and we put the fields on something called a Yee grid, which staggered their position. That let us write this center set of very easy finite difference equations. And then if we have 1,000 points in our grid, we're going to write each one of these 6 equations 1,000 times. So we'll take this equation, write it 1,000 times, which then we can cast in matrix form this way. And here's where our derivative operators and our diagonal matrices arise. And we ended up in that lecture with Maxwell's equations in matrix form. But we didn't do anything with these. We didn't learn how to solve them yet. And that is what this lecture is for. So before we get into that, I want to go back to boundary conditions for our matrices. Remind you of one thing: when a field is propagating through a periodic structure, the field takes on the same periodicity as the structure that it's in. And the fuller story is that the field is composed of an amplitude term and sort of a plane wave phase term. Well, this plane wave phase term definitely does not take on the same symmetry as the structure it's in, but this amplitude envelope certainly does take on the same symmetry. And in fact, when I say the field takes on the same symmetry as the device that it's in, isn't exactly true because of this phase term. It's this amplitude term. And remember before we described these as looking like bumpy plane waves? This amplitude term are the bumps, and then this phase term is the plane wave. Well, it's the term of the plane wave that really complicates the issue for the periodic boundary conditions. In the end, this is pretty easy to fix, but that's the term that's responsible for us having to go back and figure out something else. So here's the problem. Before we had a one-dimensional grid, or we're at least looking at a cross-section of a grid, we have E1 all the way to E5, and we wanted an E6 term out here. And we said, well, if the field really is periodic, then we should be able to use E1 in place of E6. We put E1 in our finite difference approximation, and we ended up with an additional term here. And so we wrote our derivative operator for the electric fields with this additional term here, assuming that the structure is periodic. Well, the problem with this definition is it didn't account at all for this phase term. So if we're using periodic boundary conditions, let's take the field in some unit cell. If it is periodic, I should be able to stack it onto itself and see nice continuous fields, and I don't. And that's because our wave is coming in at an angle and we have these phase discontinuities. So this tells us we can't immediately apply the same boundary condition we talked about in the last slide, because the fields on the left side of an interface do not equal the fields on the right side of the interface. And why don't they? It's because of this phase term. So we want to use E1 in place of E6. Let's look at this in the framework of Bloch's theorem. So I can write E1, now I have this amplitude term and I have a phase term. I can write E6, which has an amplitude term and a phase term. Well, not surprisingly, since it's the amplitude term that has the same periodicity as the structure that it's in, we can write that A1 has to equal A6. So these two equations now become these two equations, where I've eliminated A6 and just put A1 in everywhere. But our boundary condition requires an E6, so we want E6 now in terms of E1. So let's combine these equations, and it turns out that E6 all by itself, so this is the combined A1 times e to the j beta x sub 6, ends up equaling E1 e to the j beta lambda x, where lambda x is the period. So what this is telling us is that E1 does equal E6, but with an additional phase term. And that makes sense, since it's the phase term up here that was causing us the problems to begin with. So this is our hint now of how to fix the problem with our derivative operator. So we want to put E6 in the place of E1, but we know that we can't do that. But what we can do is put E1 in here and have that extra phase term. Now our derivative operator has a, instead of a, was a negative 1 over delta x or something like that, now it has an e to the jkx lambda x. And this gives us the ability now to include some kind of oblique angle of incidence. So this really isn't a truly periodic boundary condition, because when a field comes in at an angle, it really isn't truly periodic. It's the amplitude term that is. So there's a lot of different names for this. Sometimes you'll hear it called just a periodic boundary condition. I don't know if I like calling it that, since it's not truly periodic. You might hear it called a pseudo-periodic. Probably the best term for this is a Floquet boundary condition, or a Bloch Floquet boundary condition. And this is to remind us that we're using the Bloch's theorem and theory of periodic structures in order to implement that periodic boundary condition. So that's the full story with the periodic boundary conditions, and now you should have all the information and stuff that you will need to go ahead and write a function to build those matrix derivative operators. So you'll hand it the size of the grid, and in the case of one of these pseudo-periodic or Floquet boundary conditions, you're also going to need to give that function the k-ints, your incident wave vector, and the period of the device, so that it can incorporate those periodic boundary conditions correctly. Now back to our business at hand. We want to start with these matrix wave equations, or matrix equations of Maxwell's equations, and derive the wave equation from it. So here we are. We had 6 Maxwell's equations in matrix form. I can take the first 3 and write them in block matrix form. I can take the second set of 3 and write those in block matrix form. I can even write this a little bit simpler. If I take this column vector of all the electric field components, so remember this is a column vector of column vectors. E sub x is a column vector, E sub y is a column vector, and E sub z is a column vector. Well, let me just call this one big column vector E, and I'll put the arrow over top of it, the bold E, to remind us that this is a column vector. But the little arrow vector there to remind us that it actually has all 3 components in there. We can call this big square matrix the curl operator for the electric fields. Remember, we have slightly different derivatives operating on electric and magnetic fields, so we're going to have different curl operators operating on the electric and magnetic fields. We'll have another column vector containing the magnetic field components, and we write that here. Remember the little squigglies reminding us that these are actually normalized magnetic fields. And then we have our permeability tensor. So this big square matrix just becomes mu with the square brackets around it. So the reason that we're maintaining these diagonally anisotropic terms, the diagonal terms through the tensor, so that we can incorporate our PML, our uniaxial PML, which is anisotropic. And from last lecture, we know now that we can put things in these off diagonals, but we have the extra complication of the interpolation matrices, so we're not going to worry about that here. We're just going to assume diagonally anisotropic, and we did that to accommodate the PML. Well, now we can write our other equation this way. Here we have the curl operator on the magnetic fields, and we have a diagonal permittivity tensor. Again, we made it a diagonal permittivity tensor because we wanted to put the PML into it. Now we're ready to derive a matrix wave equation. We had our two, essentially the numerical form of our curl equations. So it makes sense then we could substitute one of these equations into the other. So for example, we could solve this first equation for the magnetic field by bringing this mu tensor over here, then substitute that expression in for H here to have an equation just with epsilon in it. And I could do it the other way around to have an equation just with H in it. So when I do that, I end up with two matrix wave equations. And both of these have this same form, some big square matrix A multiplying the column vector E, and of course equals 0 because we haven't done anything on the right hand side yet. So both of these equations are in this form. I just might have an H instead of an E here. So let's think about memory for a second. A small but maybe somewhat reasonably sized three-dimensional grid will be 20 by 20 by 100. And the reason for these dimensions will be apparent later, but we could probably get something done with this size grid. So there's actually 40,000 points in this grid, 20 times 20 times 100. Well, there's complex numbers, and we also have three field components. So it turns out we have 120,000 complex numbers in this grid, which we have to store the real and imaginary part as separate. So in fact, we have 240,000 real floating point numbers. Half of them are at the actual real numbers, and the other half are the imaginary components of those numbers. So the size of our matrix then, that would be multiplying the column vector storing these fields, is 120,000 by 120,000. That means there's 14.4 billion complex numbers in that matrix A. But computers really only ever store just real numbers, so that really is 28.8 billion real numbers. So to store all that as double floating point precision, it's almost 250 gigabytes. That is a lot of memory. The point here is we want to store these as sparse matrices. So just to store our field, one of our derivative operators, so one of our derivative operators is about 24 gigabytes. But only 0.005% of that matrix operator are non-zero elements. That means 99.995% are all zeros. So if we store it as a sparse matrix, it's only 1.5 megabytes. That's very reasonable. So 3D problems are usually too large to solve on conventional computers. And the other lesson is, even with two-dimensional problems, you definitely want to store your matrices as sparse. Now, another thing we need to talk about is that all real devices are three-dimensional, but we're about to formulate a two-dimensional code. So what on earth does that mean? Well, let's look at a real device. Here we have a ruled grating, a ruled diffraction grating. It is 3 dimensions and drawn that way. But what I see is that it repeats from left to right. So it makes sense then that we could pull out a square region here and call that a unit cell, and assume that just repeats itself infinitely along this axis. So if we were to look at that unit cell, we could draw it this way. So in the dimension in and out of the board here, that would be the z direction. We're going to assume that that is of infinite extent. On the left and right boundaries, we're going to use periodic boundary conditions. That makes this unit cell, if you will, infinitely periodic. So it tends to look like this. Now, if we then also restrict propagation to be inside of this plane, then any derivative I take in the z direction has to be 0. There's no power traveling in the z direction. There's no change in the device in the z direction. So that would mean I can set both of my derivatives in the z direction to 0. Well, if I go back to Maxwell's equations and I set all my z derivatives to 0, what I see is that these decouple into two independent modes, and I color-coded them here. So one of the modes is blue and the other modes is red. So if I separate these now, here are the blue equations, here are the red equations from above. We'll call this set of 3 the E mode, and the second set of 3 the H mode. So why do we call them that? Well, we're going to take these second two equations, solve them for Hx and Hy in terms of Ez, and then substitute those expressions in up here, so we have an equation just in terms of an electric field component. So we call it the E mode. And likewise over here, we're going to do the same thing, solve these two second equations for Ex and Ey, plug them in up here, and we have one equation just for Hz, just a magnetic field component. We'll call that the H mode. So really, even though we're performing a two-dimensional simulation, we really are talking about a three-dimensional thing. It's infinitely extruded in and out of the board, and we're probably using something like periodic boundary conditions on the left and the right. Now we want to talk about deriving the matrix wave equation. So we start off with our three equations. This is straight from Maxwell's equations, just with the z derivative set to 0. Now we're going to take these last two equations and solve them for Hx and Hy. Remember, these are matrix equations. We have to watch our algebra here. And we get these two expressions. Now we're going to take these two expressions and substitute them in up here and here in order to eliminate all references to magnetic fields, and we're going to have an equation completely in terms of Ez. So here's our equation. We do the substitutions. This is completely in terms of Ez. We turn our linear algebra crank, and here's our final form of the equation. And we factored out all the terms multiplying Ez. Well, this is of the form some big square matrix A multiplying this column vector E containing only the z components, and this big square matrix is all of this. Now, we took a really easy approach to get to this big ugly matrix. If we didn't know about these derivative operators, we'd have to be manipulating 6 different finite difference equations, rearranging terms, keeping track of all the indices, and eventually come up with a very big ugly equation that would somehow lead us to populate this, and then we'd have to somehow populate it. Well, instead, we're going to have a function that can pretty simply calculate these derivative operators, pretty simply construct these diagonal matrices, and then we just put them all together in one line of code in MATLAB, which is right down here. So this will be one line of code in your MATLAB program. That is very, very easy. And so I always like to do this. If I have a big ugly matrix that I have to build, is there any way that I can break this down into smaller, simpler matrices that I can test or I can look at to see if they're right? And so that's exactly what we're doing here. So I could also derive a similar wave equation for the H mode, and here's a summary of our wave equations for the E and the H modes. If I was going to visualize the grids, this is how I would envision them. So up top we have the E mode, and if we look at a unit cell, we'll take this one. We have one component of the electric field in the Z direction, up and down, and then we have 2 components of the magnetic fields, but they're also staggered. Remember, this is one slice off the E grid. And then, of course, this arrangement of these 3 fields repeats itself throughout the grid. and propagation's restricted to this plane. That was another condition. We can't have energy going vertically in any way. If I was to look at the grid for the other mode, I have one vertical H field here, and then two electric fields within the plane. And this arrangement of fields is also another slice through the E grid, and it repeats itself throughout the grid. The other lesson here is that for the E mode, we could define TE and TM one of two ways. In this case, we see that the electric field for the E mode is always transverse to the direction of propagation, right? Because propagation is always going to be in this plane in some direction, let's say this way, and the E field is always transverse to that. So with one school of thought, we might want to call this the TE mode. And down here, we see that this isn't the case. Now we have electric field components definitely in the direction it's propagating, but in this case, the magnetic field is completely transverse. So in the same school of thought, we might call the H mode the TM mode. And there are many papers out there that do this. In fact, in my early days, I was pointed to naming them this way, and if I had to go back, I would change it. I would actually call the E mode the TM mode, and the H mode the TE mode. And here's why. Here's the second school of thought. Now we have a wave coming in at an angle, and we have a surface normal, so we have a plane of incidence that this incoming wave vector and the surface normal define. The vector perpendicular to that is the TE mode, and the vector within the plane of incidence is the TM mode. Well, now think about this. As our wave vector comes in at 90 degrees and this plane lies down, so now our wave vector is in this plane. Well, there's a component pointing straight up now, which ends up being the TM mode. So when the electric field is pointing straight up, in this school of thought, you would call that the TM mode. This electric field would be within the plane, and in this case, you'd call that TE mode. Now, bounce back and forth a couple times between this slide and the last slide, and we're defining TE and TM opposite. And sometimes in the literature you'll read it this way, sometimes in literature you'll read it the other way. What I can say is what is on this slide seems to be emerging as the dominant convention for defining TE and TM modes. So the moral here is when you're reading the literature and you hear somebody or read somebody say TE mode or TM mode, you may not exactly know which mode they're talking about, and you'll have to dig deeper, and it's not always easy to figure out what people are talking about. Sometimes I've had to just model the device myself, try both polarizations, match it up to what they did until I finally figure out what they mean by TE and TM. Because don't assume one way or the other. Okay, so back to our matrix wave equation. It's of this form: A equals times E equals 0. Or if we did the H mode, we would have some A multiplying an HZ equals 0. So how do we solve this for E? Well, we pre-multiplied both sides by the inverse of A, and essentially we have this. E sub Z is inverse of A times 0, but that always equals 0. We call this a trivial solution, and our problem is not yet solvable. And why is this? Because we haven't told it what kind of source there is. If we don't tell it that there's a wave hitting the device, this is the math way of telling us, well, then there is going to be no electric field. You did not hit your device with a wave. So we need a source B, and it comes in on the right-hand side. And now if we solve it for the E sub Z, now we have something that's solvable. Now, unfortunately, what goes into B is not necessarily real intuitive, but we have a real neat way here of really simplifying this and incorporating about any source that you want to. But I could not be handed that B term and look at it and know what kind of source it is. It's unfortunate, it's a little bit abstract, and it's going to get a little bit weird here, but in the end I think has a really simple implementation. So we're going to talk about one special case of a source, a plane wave source coming in, hitting our device, and then scattering. So how do we incorporate a plane wave source? That's our next topic. The first thing we're going to do is divide our grid into two dominant regions. And so this little dashed line is dividing the regions. We'll have a total field side and a scattered field side. On the total field, we have both the source and the waves that are scattered from whatever object we're modeling. So the total field is physical reality. If you're testing something in the lab, it's always just a total field. Mathematically, however, we can have a region up here that does not contain the source, but anything reflected off this device can just pass right through that interface as if it's not there. So anything we see up here is purely reflected from the device. So we call that the scattered field because we're just seeing fields that are scattered. So how do we implement this? It starts off by just declaring it. Now what we have to do is make sure that our finite difference equations are consistent with that. So let's go ahead and look at our grid. We have a 2D grid, and each of these little circles is representing one point on the grid. And we know that we have finite difference equations. We have a finite difference equation associated with each point that couples each point to its neighbors. Right? Now here's the problem. Let's look at this first row in the scattered field. These are each going to have a finite difference equation, and it's going to include a term from the total field side. Well, we're writing a finite difference equation in the scattered field. All the terms should be scattered field quantities. However, at least one of them will be from the total field side. That is not compatible. Likewise, we're going to be writing finite difference equations in this first row within the total field that contain a term from the scattered field. That doesn't work. Those are not compatible. So it's going to turn out that we have these two problem rows that we need to fix to make it consistent with our total field scatter field framework. When we fix that, that is actually what injects our plane wave source into the model. But it starts off here. We're going to declare it. We're going to make sure our finite difference equations are consistent with that, and that'll be it. We'll have our plane wave source. The first step in this is to calculate your source across the entire grid without any device present. So typically, we're going to be injecting a source somewhere near the top of the grid. There will be some material present there, and the way we're formulating our plane wave source, that will have to be homogeneous. So whatever that material is where you're injecting the source, we're going to put throughout the entire grid. And so pretending that was completely homogeneous with no device or anything, what would your source look like? And we calculate that source everywhere, and we call that F sub source. So and we'll call that the source field. And so here's how you would calculate that. It's simply an exponential of e to the k dot r. So we calculate it this way on a two-dimensional grid. That's the first step. The next step is we're going to construct a matrix Q, which we'll call the scattered field masking matrix. And the way this works is we divide our grid up into two regions. We have our scattered field region and our total field region. We are going to fill in the total field region all with zeros. We'll fill in the scattered field region all with ones. Then we'll reshape this entire array of data into a column vector, and then insert that column vector into the diagonal of a square matrix. So all these off diagonal terms up here and down here are all zeros. We just have this 2D array reshaped into a 1D array going down the diagonal of the matrix. So essentially there's ones in every position along the diagonal of Q that correspond to the scattered field region in our 2D array. So now all this comes together into one simple equation where we tie it together and we calculate this vector B so that we can solve our A equals B matrix equation. Now it's not necessary that you understand all of these steps, but I would definitely expect you to understand this equation and how to implement it. So let's derive it. And this one equation, this is where all of the corrections at the boundary between the total field and scatter field are happening and being incorporated into our finite difference equations. In one very simple equation effect. So let's start up here. We have our source field. This is our plane wave source at every point in the grid as if it was completely homogeneous and there's no device, no scattering or anything. Then we have our Q matrix, our scattered field masking matrix. If we multiply these two, we get another column vector, which is the source isolated to the scattered field region. So this F sub scat is going to be zeros everywhere in the total field, but then in the scatter field it'll be just like our F sub source. Then we can do a similar calculation for the total field, where we take the identity matrix minus our Q. So this difference is sort of a total field masking matrix, if you will. It swaps the zeros and ones, and if we multiply that times our source field, we isolate the source to the total field region. So this will be zeros in all of the scattered field regions, and will be identical to F sub source in the total field regions. So what we've done is isolate the source to the scattered field region and isolate the source to the total field region. Okay, first thing, we need to correct the terms on the scattered field side. So there are terms on the scattered field side that contain total field quantities. And what we'll need to do is subtract the source from those total field quantities to make them look like scattered field quantities. So what is it we need to subtract? Well, if we multiply our original A matrix, that's the wave matrix, and that came from tying together all of our derivative operators and diagonal matrices. They all came together to calculate A. So if I say A times the field isolated to the total field region, these are the terms that need to be subtracted from those scattered field equations. However, we don't want to subtract those from every scatter field equation. We don't want to subtract that from every equation. We only want to subtract those from scattered field equations. So we have to include this Q here, which then isolates these corrections to just the scattered field region. Next, we want to correct the finite difference equations in the total field region. And some of these on the boundary contain scattered field terms. In this case, we're going to want to add those terms to make the scattered field quantities look like total field quantities. Well, what is it we need to add? It's going to be A times the source isolated to the scattered field region. But we don't want to add these everywhere. We only want to add them to the total field equations. So we need to isolate it, those corrections, to the total field region. So here's the total problem. We have A times E, and that should be a lowercase e. I apologize for that. So A times E, and here we're going to subtract this quantity, where these are the corrections on the scattered field side. Then we want to make the corrections on the total field side. Then if we do some algebra, we end up with this final equation, A times E, blah, blah, blah. So this is our B vector. Q times A minus A times Q times F source. So that is how we do it, and that is incorporating the corrections that match the finite difference equations that cross that interface between the total field and scattered field region. So let's visualize the data. So the first thing we do is we calculate our source at every point in the grid. Then we're going to build another grid array where we're going to put ones everywhere we want to be a scattered field quantity. So a very typical thing to do is to have the edge of your grid be the scattered field, particularly where we're placing our PML boundary conditions. And then just for fun, I also added a smiley face where the gray regions will also be scattered field quantities. Well, if I take this B vector that we've calculated on the last slide and reshape it back to a 2D array and visualize it, we see we only get numbers at the boundaries between the total field and scatter field. And so this has incorporated the corrections, and it's only at the boundary that the finite difference equations cross the boundary, and you end up with incompatible terms. So that's why we have numbers at the boundaries but not anywhere else. The finite difference equations out here don't cross the total field scatter field interface, so no corrections are necessary. Let's look at what comes out of some representative simulations, although simple ones. So we're going to build an array with all air. So whatever plane wave we have should just pass through without reflecting off of anything. Maybe we define our scattered field to be just the top region and the total field to be the bottom region. This is very typical of how we'll do things. So if I simulate it, here's what we get. We don't see anything up here in the scattered field. And why not? Because there's no devices down here for the wave to reflect off of. So we don't see anything up here. But we do see our interface here between the total field and scatter field, and we definitely see our source. And down here, we see it getting absorbed into the PML, which is exactly how a PML should behave. So now instead of having pure air, let's have air at the top, and then down at the bottom we have something with refractive index 3.0. We know analytically this will give us a 25% reflection. So let's see what happens. We're not going to see the source up here, but we see something else. Let's think about what that is. Down here, we have the same wave that we had on the left that's applied, and it hits this interface. Well, some of that is going to reflect, and it's going to reflect off in this direction. So what you're seeing here is the interference between that applied wave and the reflected wave. Now let's go up here. All we're seeing is that reflected wave, because that's the scattered field region. We don't see the source. We've essentially removed the source from the total field down here so that you only see what's reflected. Now let's look on the other side of the interface. We see the refracted wave. We also see that the wave is compressed because it has a higher refractive index. It's traveling slower, and this also gets absorbed into the PML. So this is exactly what we would expect to see with the same shape of total field, scatter field. This is the same basic thing, but I'm showing off here and included a smiley face. So now, in addition to having the top be the scattered field, we have an additional scattered field here. Well, over here, again, there's nothing for the field to be reflecting off of because we're modeling all air. So there are no scattered fields, so we just see 0 everywhere we've defined to be a scattered field quantity. But everywhere there's a total field, we see our initial source. Now let's go over here where we have this interface where a wave will come in and reflect. So we have this applied wave, and then it gets reflected. Well, we only see the scattered fields inside the smiley face, except in the mouth and the eyes, which are defined to be total field. And we definitely see this bumpy region where it's the interference between the applied wave and the reflected wave. We see the same transmitted field here, the refracted wave. It also gets absorbed into the PML. And we see the same reflected wave that gets absorbed into the top PML. But what's neat about this equation we have is that we can arbitrarily shape our total field and scatter field very easily and tie it all together with one simple equation. Another thing I'm not mentioning in here, but is very cool, if we went to higher order accurate derivatives, 4th order accurate, 6th order accurate, so our finite difference equations now couple a point in the grid to somewhere way off, maybe even 2 cells away, that equation still works. Now let's summarize the formulation and look at some examples. We're not stepping through the code here, we're just looking at examples of the output of these so you can get a feel for what this looks like. So here's the summary all in one slide. We are going to divide our grid into these 2 regions, the scattered field and the total field region. And our source, it's effectively a one-way source at this boundary that gets injected toward the device, and then the fields scatter, and anything that may get reflected passes through that interface as if it weren't there. And so any field up here has to be reflected. We're not going to see the source. We started with Maxwell's equations, and we derived the matrix wave equations, and these 2 matrices A came out of that. Then we learned how to calculate the source vector on the right-hand side of our equation. First, we calculated the source field everywhere, as if the entire grid was homogeneous. We constructed this scattered field masking matrix that has 1s down the diagonal and all the positions corresponding to scattered field regions. And then in one equation, we calculate this vector B, which goes on the right-hand side of our equation. Now these are equations we can solve for either E or H. And the A up in this equation is just one of these two, depending which mode we're modeling. But this equation is the same. And once we have B, now we can solve these for our field. In this class, we're mostly going to be modeling periodic structures, and our grids are going to look very similar to this. We are going to have our device in the middle, and there's going to be some space between the device and the PML. Our source fields are going to look very much like this. We're going to be injecting the plane wave in air, dielectric constant of 1. So in this array, we're essentially having a dielectric constant of 1 everywhere, and what would our incident wave look like if calculated everywhere? So that's our source field. Then we define our total field scattered field regions, and the total field scattered field interface just has to be above the actual device somewhere. And then when we calculate the fields from this, they look like over here. And we can notice that there's some kind of discontinuity happening here. And what that is that's the interface between our total field scatter field. And in this region, we're looking at both the waves applied to this diffraction grating and the waves reflected from it. On the other side of the interface, we really only see the waves reflected from it. And down here, we're only seeing the waves transmitted through it. And again, there's like another line here, an apparent discontinuity. And what we're looking at here, and it probably starts more around here, is the PML. And it's absorbing the outgoing wave. Likewise, down here, we can tell that our PML starts somewhere around here, and it absorbs that transmitted wave. We don't have to have just plane wave sources. We can have other types of sources. So let's say we want to have a cylindrical source. What does a cylindrical source look like in air? We start off just by putting air everywhere. This would be our source field, as if there was air everywhere. How would that look? Then we define our scatter field, total field to look like this. And notice I'm going to put some scattered field around the actual source. So our source would fall right in the middle of this. Then if I simulate that, there's just air everywhere. Nothing is being scattered or reflected, so I don't see anything inside here because it's a scattered field region. I also don't see anything outside. I just see the source. Well, now let's put an object here, same source. So we have an object. Over here where I'm calculating the source field, I don't have an object because it's all homogeneous. I'm going to use the same definition of total field scatter field source and make it look this way. Then if I simulate it, look what happens. Suddenly I see something inside this scattered field region because something is reflecting off of our object. I also see energy out here because it's being reflected from the object. We can also have modal sources. Remember when we looked at waveguides, we calculated modes. And this was something I actually did some time ago where I was simulating an optical fiber, and there was also a dielectric slab I was modeling, but we have a core region surrounded by a cladding, and I was wondering what happens when you angle the end face. Because at the time I was trying to prevent reflections. So what do we do first? We calculate the source field. This is the source field that exists everywhere. And so what we see is it's just this mode source confined to the core propagating this direction. Well, now I define my total field scattered field regions this way. And when I tie all this together with the B equals AQ minus QA, this is what I get. And I can see the little discontinuity here, and that's the boundary between my total field and scattered field. And I see I get some kind of strange reflection here at the interface. Okay, so we've modeled something, and we know the field now. What we want to do is post-process that field to calculate meaningful information. So one thing that is very meaningful is transmittance and reflectance. Remember how we define that. Transmittance is the fraction of power from the applied wave that ends up being transmitted, and reflectance is the fraction of power that ends up being reflected. Here's the overall process. You run your simulation and you know the field. Then we're going to extract cross sections on the reflected and transmitted sides. So it's only one little row across the grid for the transmitted side and one little row for the reflected side. Then from these 1D arrays, we're going to calculate the wave vector components that will be associated with our spatial harmonics. And then we're going to FFT these things that we extracted, and the answer from that FFT will be the amplitudes of those diffracted harmonics. Then we can calculate the diffraction efficiency of each of those harmonics. Then we add those all up to get overall reflectance and transmittance. And then the final thing is calculating the conservation of energy and making sure we get 100% of our energy back. So here is the basic way that we construct our grid. We'll have a device, and there's definitely going to be some space between our device and the PML. We'll get more into why that is later. Suffice to say is that evanescent fields within this device, if they're allowed to touch the PML, we run into problems. And we'll talk more about that. But there's going to be space, and it's about a wavelength. We call those the spacer regions. Then we have this total field scatter field interface. So in this green row, that's going to be the origin of our source. That'll be the first row that we see that in, and the source will be directed down at the device. Then what I want to do is have some place above that total field scatter field interface, so we're only in the scattered field region now. So if there are any fields here, they have to be purely reflected. There's no source here. And this is where we're going to extract the fields. We don't want this on top of our PML, because by the time we get inside the PML, the waves are starting to be absorbed. And if we calculate reflected power there, we're going to count for less energy than there really was. So there needs to be a small space between our total field scatter field interface and where we place the PML, because that's where we're going to be calculating the reflected fields. Now, past the device, somewhere close to but not inside the PML, is going to be where we're going to record the transmitted fields. Okay, so here's our grid. When we're done calculating the field, we'll look at this row and we'll store those fields in a 1D array. And we'll do the same thing on the transmitted side. We'll extract the fields, not from inside the PML, but pretty close, and store those in a 1D array. So at this point, we calculate the fields and we extract two 1D arrays that are cross sections through our grid. One of them will be the reflected field, one of them will be the transmitted field. This is a busy slide, and I apologize for that. So this could be one of our extractions, either transmitted or reflected, doesn't matter. Each one of these will end up becoming a spatial harmonic in a following step. So each one will have a set of wave vectors associated with it. So first we'll calculate the transverse wave vector, the one in the x direction, and in our grid, x direction is left and right. So we have something periodic, so in fact there's an infinite number of these. However, if our grid is only 20 cells wide, we're only going to be able to calculate 20 possible values. So one thing we want to do is make sure we have an odd number of cells wide that our grid is. So here's big NX, this is the number of cells wide. And we want to make this something like 11. And then this integer m will go from -5 to +5. Since we pass through 0, that makes it an odd number, and that's why we want an odd number here, so that we pass through zeros and have just as many positive harmonics as we do negative harmonics. So we're going to make the number of cells wide an odd number. Now, these transverse wave vector components are constant throughout the grid. They never change. So how do we calculate the longitudinal components on the reflected and transmitted sides? Well, from the dispersion relation, right? If these really are nice linear homogeneous isotropic materials, the magnitude of the k vector is fixed. So if we know half of it, the x component, the transverse component, and the overall magnitude is fixed, we get the longitudinal components. In this case, the y direction up and down. So at this point, we have a 1D array containing the y components on the reflected side of the incident, or of the wave vector, not the incident wave vector, And we also have a 1D array containing the longitudinal components of the k vector on the transmitted side. And also we're storing this kx, which is the transverse component throughout the entire grid, in another 1D array. So we're coming away from this slide with 3 more 1D arrays. The transverse components that exist everywhere, and the longitudinal components on the reflected and transmitted sides. Now we calculate the amplitudes of our spatial harmonics. So we may be modeling something like this, but we've probably wrapped our grid around one of the unit cells, and we extracted, let's say, the field in one of those cross sections. Well, this field is periodic. It can be decomposed into a Fourier series that we talked about, and the amplitudes of each of these terms in the Fourier series is an amplitude of one of our spatial harmonics. So all we do is we take this one period of the function, we FFT it, calculate the fast Fourier transform, and the array that comes out are the amplitudes of these spatial harmonics. So here we're showing blue for the transmitted side. We simply FFT that, and the new array that we get are the amplitudes of the spatial harmonics. Now the number of elements in this 1D array will be the same as the number of elements over here. So if our grid is 11 points wide, we're only going to be able to calculate amplitudes for the 11 lowest order spatial harmonics. In principle, there's always an infinite number. However, experience shows us that the power is always in the lowest order of those. So we can ignore the higher order ones. So at this point, we have all the information we need to calculate diffraction efficiencies. We have a 1D array, which is our longitudinal component from the reflected side. We just did our FFT, so we have another 1D array, which is the amplitudes on the reflected side. We have a single scalar number, which is the amplitude of the applied wave. And we have another single scalar number, which is the z component of the incident wave. If we calculate this equation, we come out with a 1D array, which is the diffraction efficiency in each of the reflected spatial harmonics. Same thing on the transmitted side. This KZTRN, this is a 1D array containing the longitudinal components on the transmitted side. This is a 1D array of the amplitudes of the spatial harmonics on the transmitted side. We have a single scalar amplitude of the plane wave, single scalar z component of the incident wave, and then we have the relative permeabilities in the reflection region and the transmission region. And both of these are just single scalar numbers. Well, we come out with another 1D array which has the diffraction efficiencies of all the spatial harmonics on the transmitted side. Now, using this equation, remember, this assumes that we have calculated electric field quantities. S we're using as the amplitude of electric field quantities. This equation changes, if you recall, if for some reason we calculated magnetic field quantities. That would happen if we're solving for the H mode. So in which case we got to go to that previous lecture and grab the correct equation. So now we know all the diffraction efficiencies of the reflected waves, all the diffraction efficiencies of the transmitted waves. So to get overall reflectance, we want to add up all of the diffraction efficiencies of the reflected waves. Now what we come out with is just a single scalar number representing how much power overall is being reflected. The same thing on the transmitted side. If we add up all the individual diffraction efficiencies, we end up getting a single number which tells us how much power is transmitted. Then the last thing to do is always good practice. Add reflectance and transmittance, and as long as there's no loss or gain incorporated, we should get 100% of our power back. And this is an extremely good check to make sure things are working. Now, if we get 100%, that does not mean for sure that your code is working, but if you don't get 100%, then we're absolutely certain that your code is not working. And if you do have loss or gain built into your model, I always suggest, okay, build that in, get everything working, but in your final check, turn the loss or gain off for a moment. Run your simulation, make sure you get conservation of energy, and then you're just one more level of security that your code really is working. So that's it for this lecture. In the next lecture, we're going to go one step at a time and step you through the algorithm of finite difference frequency domain. This lecture was the formulation. This is where we got equations flying all over the place. Next lecture is where we tried to bring peace and harmony to this, and we'll go one little step at a time, step 1, 2, 3, 4, 5, and I'll show you every little detail of a simulation.